Somewhere, right now, at this exact moment, there is a controlled explosion happening inside a building. Not an explosion like a bomb, something far stranger, far more precise, far more powerful. Inside a sealed chamber, atoms are being split apart, and when they split, they release energy, not chemical energy like burning coal or gas, something fundamentally different, something that comes from inside the atom itself, from the force that holds the universe together at its most basic level. And that energy is being used to boil water. That is it. That is nuclear power. The most complex, controversial, and misunderstood energy technology ever built by human beings. And at its core, it is a very sophisticated way of making steam. But the path from splitting an atom to lighting your house is one of the most remarkable stories in the history of science and engineering. And today, we are going to walk through every single step of it. How nuclear power actually works, what is really happening inside a reactor, why it is so powerful, what makes it dangerous, and why some of the smartest energy scientists on Earth believe it might be the most important technology we have for the future of human civilization. Let's start at the beginning. And the beginning is very, very small. Everything you can see, touch, taste, and breathe is made of atoms. Atoms are almost incomprehensibly tiny. A single strand of human hair is roughly 1 million atoms wide, and inside every atom is a nucleus, a dense core made of protons and neutrons packed tightly together. And holding those protons and neutrons together is one of the 4 fundamental forces of the universe. Scientists call it the strong nuclear force. Here is what makes this force extraordinary. It is the most powerful force in nature, far stronger than gravity, far stronger than electromagnetism. It is an almost unimaginably powerful glue that holds the nucleus of every atom together, and it is extraordinarily difficult to overcome. But for certain very large atoms, the ones at the heavy end of the periodic table, the nucleus is so large, so packed with protons and neutrons, that it becomes slightly unstable. The strong force is still holding it together, but it is working hard to do it. These heavy, unstable atoms are always on the edge of breaking apart, and some of them, with just a tiny push, will split. The most famous of these atoms is uranium 235, and the tiny push is a neutron. When a free neutron traveling through space strikes a uranium 235 nucleus, something extraordinary happens. The nucleus absorbs the neutron, and then it becomes so unstable that it splits. It tears apart into 2 smaller atoms and releases energy, a tremendous amount of energy compared to the mass involved. Energy that was stored in the strong nuclear force itself. But here is where it gets truly remarkable. When that uranium nucleus splits, it does not just release energy, it also releases 2 or 3 more free neutrons. Those neutrons travel outward, and they can strike other uranium nuclei, which split, and release more neutrons, which strike more nuclei, which split. This is a chain reaction, self-sustaining, self-propagating, each split triggering more splits, triggering more splits. If you let it run completely unchecked in a large enough mass of uranium, it becomes a nuclear explosion, the most destructive force humans have ever unleashed. But inside a nuclear power plant, the chain reaction is not a bomb. It is a controlled simmer, a precisely managed, carefully regulated process that releases that energy slowly and continuously. And that is the engineering achievement that makes nuclear power possible. So how do you control a chain reaction inside a reactor? The answer is one of the most elegant pieces of engineering in existence. Inside the reactor core, the uranium fuel is arranged in long, thin metal rods called fuel rods. These rods are bundled together and submerged in water. Between the fuel rods sit another set of rods called control rods. These control rods are made of materials like boron or hafnium materials that absorb neutrons. They are neutron sponges. When you push the control rods down between the fuel rods, they absorb neutrons and slow the chain reaction. The more you insert them, the slower the reaction gets. Pull them out and the reaction speeds up. It is a physical throttle for nuclear fission. Precise, reliable, adjustable. The water surrounding the fuel rod serves 2 purposes simultaneously. First, it acts as a coolant, absorbing the tremendous heat generated by the fission reactions. Second, it acts as a moderator, The neutrons released by fission are moving extremely fast, and fast neutrons are actually less effective at splitting uranium. 2, 3, 5. The water slows the neutrons down to what physicists call thermal speeds, and slow neutrons are far more efficient at triggering fission. So the water makes the chain reaction more efficient, while simultaneously cooling the reactor. Finland is currently the world leader in solving this problem. They are building a permanent deep geological repository called Onkalo, which means hiding place in Finnish, carved deep into ancient bedrock that has been geologically stable for billions of years. The facility is designed to safely contain nuclear waste for 100,000 years. It is arguably the longest-term engineering project in human history. The newest generation of nuclear reactor designs, called Generation 4 reactors, includes designs that could actually use existing nuclear waste as fuel, transforming one of the technology's greatest liabilities into an energy resource. These designs are still largely in development, but several are moving toward demonstration phases in the coming decade. And then there is fusion, the holy grail, the thing that nuclear scientists have been chasing for 70 years. Everything we have discussed so far is fission splitting heavy atoms apart. Fusion is the opposite, smashing light atoms, specifically hydrogen isotopes, together so hard they merge into a new, heavier atom and release enormous energy. This is what powers the sun. This is what powers every star in the universe. Fusion produces no long-lived radioactive waste, cannot melt down, uses fuel derived from seawater in effectively unlimited quantities, and produces more energy per reaction than fission. The problem is that achieving fusion requires temperatures of over 100 million degrees Celsius, hotter than the core of the sun. Containing plasma at those temperatures requires either massive magnetic field containment systems or incredibly powerful laser arrays. For decades, the joke in the physics community was that fusion power was always 30 years away, and always would be. But something shifted in December of 2022, when researchers at the National Ignition Facility in California achieved fusion ignition for the first time in history, producing more energy from a fusion reaction than the laser energy used to trigger it. It was a milestone that many physicists had spent their entire careers working toward. Commercial fusion power remains years away, but for the first time in the history of the technology, the scientific barrier has been crossed. The atom that powers stars, the energy source that runs on seawater, the technology that could provide clean, unlimited power to every human being on Earth. That future is being built right now in laboratories and reactor sites around the world. And it all started with a neutron hitting a uranium nucleus, an atom splitting, and a tiny piece of the strong nuclear force that holds the universe together being converted into light, heat, and the electricity powering the screen you are watching this on right now. One substance doing two critical jobs. The heat absorbed by the water in the reactor core turns it into steam. Or in many reactor designs, the hot water under pressure transfers its heat to a separate loop of water which turns into steam. And that steam spins a turbine. The turbine spins a generator. The generator produces electricity, which travels through power lines to your home. Atom, split, heat, steam, spin, electricity. That is the full chain. Now let's talk about the fuel itself, because most people have a completely wrong picture of what nuclear fuel looks like. When most people hear uranium, they picture something glowing green, something visibly dangerous, something that looks radioactive. Real uranium fuel pellets are small, dark ceramic cylinders about the size of your fingertip. They look almost unremarkable, like small, dark gray pebbles. Each one weighs about 10 grams. And each one contains as much energy as roughly 1 ton of coal, a single ton, from something you could hold between 2 fingers. Those pellets are stacked inside long metal tubes called fuel rods. Each fuel rod is about 12 feet long and less than half an inch in diameter. Hundreds of fuel rods bundled together form a fuel assembly, and a reactor core contains hundreds of fuel assemblies. The energy density of nuclear fuel compared to any other fuel source is almost beyond comprehension. Natural gas, coal, oil, all of these release energy by breaking chemical bonds between atoms. Nuclear fuel releases energy from inside the atom itself, from the strong force, from the fabric of matter. The difference in energy density is not 10 times or 100 times. It is millions of times more energy per kilogram. Now let's talk about safety. Because this is where the conversation around nuclear power always gets complicated and emotional. And it deserves a clear, honest look at what the actual risks are. A nuclear power plant cannot explode like a nuclear bomb. This is one of the most persistent and damaging misconceptions about nuclear power. The uranium fuel in a reactor is not enriched enough to create a nuclear explosion. The physics simply do not allow it. What can go wrong in a reactor is a loss of cooling. If the coolant water is lost, or the cooling system fails, the reactor core can overheat. The fuel rods can melt. This is what happened at 3 Mile Island in 1979, at Chernobyl in 1986, and at Fukushima in 2011. Chernobyl is the word that haunts nuclear power more than any other, and it deserves serious examination. The Chernobyl disaster was caused by a combination of a fundamentally flawed reactor design that only the Soviet Union was using, and a catastrophic series of human errors during a safety test conducted at night by undertrained staff. The reactor had a dangerous characteristic called a positive void coefficient, meaning that if cooling water turned to steam, the reaction actually sped up rather than slowing down. Modern Western reactor designs have the opposite characteristic. If cooling is lost, the reaction slows automatically. The physics themselves create a safety response. Fukushima was caused by a once-in-a-millennium earthquake, followed immediately by a massive tsunami that destroyed the backup power generators needed to run the cooling pumps after the reactor shut down. The reactors did what they were supposed to do. They shut down automatically when the earthquake hit. But keeping a shut-down reactor cool still requires power, and that power was destroyed by the tsunami. These disasters were real. The consequences were serious. But the data on nuclear power's actual safety record, compared to other energy sources, tells a story that most people have never heard. Studies by major energy research institutions consistently show that nuclear power causes fewer deaths per unit of energy produced than coal, oil, natural gas, and in many analyses, even fewer than solar and wind, when manufacturing, accidents, and installation fatalities are included. The fear of nuclear power is real and understandable. The statistical reality is more complicated. Now let's talk about what happens after the fuel is used. Nuclear waste is one of the genuinely difficult challenges of nuclear power. Spent nuclear fuel is intensely radioactive and remains hazardous for thousands of years. Currently, most spent fuel is stored in deep pools of water at reactor sites or in dry cask storage containers. These methods are considered safe for current timescales, but the long-term solution of permanent deep geological disposal has been politically and logistically difficult to implement at scale.